Okay, so here's where we left off last time. We were talking about matrix operations. We ended with how to multiply a matrix times a vector. So we're going to pick up from there. So next question, how do you multiply two matrices times each other? Now, again, let me remind you, you probably saw, or you may have seen a formula for this in high school. We are momentarily forgetting about that. We are momentarily setting that aside because that probably got into your head in the form of, a dictate from your teacher with no justification or motivation given at all, right? And I don't want that to be how matrix multiplication resides in your mind. I want you to have a better intuition for why it ought to be true. So, I'm going to start this presentation with a reminder about what composition of functions is. This is how we talk about composition of functions. It says whatever comes out of one function, right? We've got a function t from Rn to Rm. Whatever comes out will then go in to the next function, s. Okay, so here we're composing these two functions, t first and then s. Note that we write this. This is very counterintuitive at first glance, but I'll explain why this is the case in a couple seconds. We write this as S compose T. From looking at the diagram, you'd think T compose S. Right? It's not. It's S compose T. Okay. And the reason why is if you look at the formula for, how do you write this down? The composition of two functions. How does that act on an input vector x? If you write it down using function notation, notice because T acts first, it is on the right. It's the one that's closest to x because it's acting on x first, right? And then the s has to be on the left because it acts second. So, it's a weird situation that we're in. When we write a composition of functions using the little circle like that, do we order them in such a way that's consistent with function notation, or do we order them in the way that's consistent with the diagram? We have to go with the function notation because it is itself function notation, right? So you have to do this. Be aware that it seems to be backwards when you look at the diagrams, right? When you're thinking about the actual order of that things go. It's not left to right, it's right to left. Okay, all right, keeping that in mind. Okay, so here's a composition of two linear transformations. Now let's suppose that T is represented by some matrix A. Recall, that's what a matrix is. A matrix is a shorthand representing linear transformation. Suppose S is represented by a matrix B. Again, that's what a matrix is. So let's say it's the shorthand for S is B. Well, this composition, this is also a linear transformation. It's going to be represented by some matrix. Let's momentarily call it C. And but then let me scroll down to this. Oh, I can't quite fit that on the page. Let me scroll down to this observation here. Wouldn't we like for that to be true? I mean, look at the way we've written the right-hand side of this equation, B times A times X. Man, we would love to be able to say that that's equal to BA, the product of two matrices, times X. I mean, if that wasn't true, algebra would just be unthinkably difficult to deal with, right? So now this does not have to be true. Right? We certainly haven't proved this to be true, but we want it to be true. Right? So if this is going to be true, if this is going to be the case, if the product of two matrices is going to be associative in this sense, right? Then look what we have to do. We really, this being a shorthand for that, we really have to let the product of two matrices be the matrix representing the composition of two linear transformations. You just kind of have to do it. So that's going to be our motivation. We recall that we defined matrix vector products based on, but let's think in the context of linear transformations. What should it mean? Right? And we're really kind of morally doing the same thing here. What should matrix multiplication mean? Well, it really should mean the composition of two linear transformations. So that's going to be our definition. well, it's going to be our motivation for our definition. We're going to motivate matrix products as being whatever matrix it has to be that represents, as a shorthand, the composition of the two linear transformations. Okay, all right. So, how do we actually write that down? So here's our motivation right there. So suppose we have two matrices, and again, I don't want to have to, every single time I do this, I don't want to have to say, okay, I got to take A, I have to reverse engineer what the transformation T is. B, okay, I'm going to reverse engineer what the transformation S is. I'm going to plug them in and compose the two big linear transformations, and then try to figure out what matrix represents it. That's going to be tedious. So I would like to figure out a way to accomplish the goal we just talked about, but just only looking at the matrices themselves, right? I want to get the same answer that I would have if I composed the linear transformations. I just don't want to do that legwork. Okay, so we're going to need to be making reference to the rows of the A matrix. That's the notation that we're going to use, capital A sub whatever, whichever row you're referring to. We're going to use lowercase to represent columns. Likewise for the B matrix, rows in capital, columns in lowercase. Okay, and here's how our calculation goes. We're going to compute this product matrix. We're going to do it one column at a time. It ends up being convenient to do it one column at a time. And we're going to get an answer that we'll be able to interpret. But let's go through the process. Here we go. Columns are images of standard basis vectors. Now this is, we talked about this. This is our definition of a matrix. You have a matrix representing a transformation. The A represents S composed T. The columns are just the images of the standard basis vectors. That's our definition of a matrix. And then everything else is just kind of downhill from here. Here's what it means to compose two functions. Right? That's what T does to a standard basis vector. T on any vector is just the matrix A times the vector. Which, of course, we know gives us the corresponding column of the A matrix. So, altogether then, what we've got now is a formula that tells you about the product of two matrices. I'm going to tell you about how to multiply B times A by in terms of a product that we already know how to do. Only a matrix times a vector. So a column of a product matrix is computed in terms of matrix vector products like this, which of course now we have different points of view on how to multiply a matrix times a vector. The point of view I want to take here is that the columns of this product are linear combinations of the columns of the left matrix. Right? B is the left matrix. Linear combinations of the columns of the left matrix with the coefficients of the vector, the corresponding column of the right matrix, as being your coefficients. Okay. All right. And that gives us our first interpretation. This is our primary, I'm going to say, way to think about how to multiply a matrix times another matrix. If you want to look at the product matrix BA, how do you compute BA? Well, we're going to take the left matrix. We're going to look at the columns of that left matrix. We're going to take linear combinations of those columns where we then use the corresponding column of A, our right matrix, as the coefficients. We are basically cornered into choosing this as our definition. This definition about columns of the left matrix, linear combinations of the columns of the left matrix, where you use the corresponding column of the right matrix as your coefficients. This is how you multiply a matrix times a vector, linear combination of the columns. This vector gives you your coefficients, right? And that we have to do because we already decided we wanted matrix multiplication to relate to compositions. So, like I say, it's almost like we have no choice. Technically we have a choice, but this is the only reasonable choice to make. Now, you can take a different point of view on this. You can interpret this as dot products, right? Now again, that's the point of view that students saw in high school most of the time. How to multiply a matrix times a vector. You do dot products with the rows of the matrix. That gives you a different way to think about matrix multiplication. And that's the one I'm going to write down here. I'm writing this as being the definition, you'll notice. I don't encourage this as the primary way to think about matrix multiplication. I'm writing this as the definition because it's the easiest one to write down. I mean, it's just easier. The notation is more convenient, and so that's handy. Right? And look, very often, when you're multiplying matrices, taking corresponding rows of the left matrix, the corresponding columns of the right matrix, and doing dot products. Yeah, absolutely. It's very convenient. Right? Again, this follows immediately from thinking about this as dot products. Rows of the left matrix. And notice that AJ is the corresponding column of the right matrix. Okay? So it's fine. But really, I think you'll find certainly later in the course, and even more so in Math 216, that what I have highlighted in red here, this is really the more valuable point of view, more valuable way to think about matrix multiplication. Linear combinations of columns of the left matrix. Okay, a third point of view that you can take, and this is just a matter of looking at either of the above and thinking about components and just taking a different point of view on it. A third way to do it is you can think of this product as being the process of taking linear combinations of the rows of the right matrix. And we're going to go through an example of that in a couple seconds here. Okay, so first, linear combination of columns. Here's a matrix product. Let's compute the first column, which I'm gonna cover so we don't give it away. Right? I'm going to compute that. Excuse me. I'm sorry, I highlighted the wrong thing. I want to multiply this out. We want to compute the first column of the product matrix. How are we going to compute that first column of the product? Well, we're going to use the formula above, and that first column is a linear combination of the columns of the left matrix. This is always the case. We're always taking a linear combination of the columns of the left matrix. Now, what coefficients are there in that linear combination? I claim that this green is a linear combination of the two blue columns. Okay. With what coefficients? You use the corresponding column of the right matrix to give you your coefficients. So in this case, 5 and 6 are our coefficients. And you multiply that out, you get this. That's the first column of the product matrix. Everybody see the process? It's a lot like matrix vector multiplication. It's just you just have to pick the appropriate column of the right matrix. Likewise, for the second column, if you want, here, let me get rid of that. If you want to compute the second column over here, that's going to come as well a linear combination of the columns of the left matrix. Here they are again, same columns of the left matrix. And now, since I'm looking at the second column of the product, I use the second column to give me my coefficients. And you punch that up, and that gives you this. That's the second column. So, straightforward process. And notice that this first column, this second column gives us our product. Now, you can confirm, if you're uncomfortable with this process of what we did here, you can confirm by doing it the second way. You can take these exact same matrices and, row dot column like you're accustomed to. So, for example, how would I compute the top left element of the product? Well, I take the top row of the left matrix and the left column of the right matrix. Do that little dot product, boom, there's that 23. Note that's the same 23 that we got doing it with linear combinations. So it's identical arithmetic. In fact, you can even see that dot product in the linear combination. Right? This dot product, 1 times 5 plus 3 times 6, here it is. 1 times 5 plus 3 times 6. 1 times 5 plus 3 times 6. It's identical arithmetic. It's just sort of bookkeeping in a different way. Okay. All right, etc. From a point of view of linear combinations of rows, you go with the right matrix. So the first row of the product we compute as a linear combination of the rows of the right matrix. Like so. And I color-coded wrong there. I want to compute these. So linear combinations of the rows of the right matrix of 5, 7, and 6, 8. We use as our coefficients, the corresponding rows, the elements in the corresponding row of the left matrix. That gives you the 1 and the 3. And again, you punch up that linear combination and bam, there's the same 2 entries that we already computed twice already. Okay. All right, so that's how matrix multiplication works. Bunch of exercises for y'all on that. But the main thing I want to call your attention to in this process is that these various different points of view that we have, whether you're thinking about linear combinations of the columns of the left matrix, or linear combinations of the rows of the right matrix, or dot products of the rows of the left matrix with the columns of the right matrix, whichever point of view you want to take, it all comes straight out of matrix vector products immediately as a consequence of having chosen that we want matrix multiplication to correspond to composition of linear transformations. So this is really the big point, is that whatever little game you have that allows you to compute matrix products, you're composing linear transformations. That's why it's natural. That's why we choose this cosmetically weird formula for matrix multiplication. Cosmetically weird, but it's very natural in terms of what it represents. Okay. Moving along. So we're now done with Chapter 3. Chapter 3 is a really short chapter. Right? I just needed to give you all just enough linear transformation for us to be able to use linear transformations with matrices in order to talk about derivatives in a more powerful way. And it's going to make a big difference. That said, we're going to set that aside for the moment, and we're going to go on and do some fundamentals of derivatives. I'm going to start with single variable derivatives. I want to remind you all of a couple of things about single variable derivatives. Emphasize single variable derivatives. I know y'all already had Calc 1 classes. This is how I want to go forward thinking about single variable derivatives. Now, y'all probably already have a favorite way to think about single variable derivatives. I have a strong suspicion that slope of the tangent line is number 1 on your list of best way to think about derivatives. And I want to pull you away from that. Slope of the tangent line, let's think it through a little bit here. Slope of the tangent line to what? Slope of the tangent line, well, to the curve. The curve representing the function, the graph. Right? Thinking of derivatives as slopes of tangent lines assumes that the curve you're looking at is the graph of the function. Said differently, this interpretation of derivatives only makes sense if you're looking at a graph of a function. And as you all recall from our several days in Chapter 2, graphs are of pretty limited utility in a multivariable calculus class. I mean, pretty limited. Right? I mean, there's only a very, very small number of situations where you can even draw the graph. So I don't think it's a good idea to hang your hat on. So what I want to do is, again, I'm going to ask you to temporarily set aside this point of view that you have on derivatives as being slopes of tangent lines. Don't throw it away completely. There is a point of view in the multivariable context. When we start talking about graphs, derivatives in a graph context, it won't be today. But there is a situation where, a slope of a graph is going to be one point of view on one kind of derivative that we're going to talk about. But the vast majority of stuff that we're going to do with derivatives is not going to be about slopes. So, like I say, set that point of view aside. Here's a couple of points of view, or really depending on how you think about it, one point of view on a derivative that really does translate over to the multivariable context extremely naturally. And that is, let's look at these one at a time. This formula here, this first one, you see is just kind of a rewrite of our linear approximation. Y'all remember the formula for linear approximations? Right, this is an old Calc 1 formula. This is very closely connected to the equation of the tangent line. If you want to think about it in the graph context, that's fine. But let's think about it as a linear approximation to the values of a function. And you take the little f of x, you move to the other side, do that as a change in f, delta f, and what you have is that the derivative can be thought of as something that you multiply by the change to the input of the function to get a good approximation to the change of the output of the function. Okay. So, succinctly, we're thinking of a derivative here as a factor. Don't think of it as a slope. Forget about slopes. Notice I'm not even saying to think of it as a fraction. I mean, the notation looks like a fraction. We don't want to think of it as a fraction. I want to think of it as a factor. It's something you multiply by one thing to get another thing. Okay, let's look at the chain rule. Y'all remember the chain rule here. There's different ways to write the chain rule, different ways to interpret it. Here, I'm thinking that we've got some function, f. Notice I'm not drawing a graph. And I'm considering that I've got some point here, x, in the domain, and it's moving with some velocity, dx dt. Well, look, every point in the domain is going to have an image in the target. Different points have different images. So as this point in the domain moves, the image in the target's going to move as well. So you could reasonably ask if x is moving in the domain, then how fast is f of x moving in the target? Right? So again, I'm thinking of, in this situation, I'm thinking of the derivative as a factor. I'm thinking of it as something that you multiply by a velocity in the domain, the result of which will tell you the velocity in the target. Okay, so it's a different way to think about it. It's one of several ways that you've previously thought about the chain rule. This is the way I want to interpret the chain rule in this context. Okay, so the point of view I'm going to take on both of these equations, though. In both cases, note that the derivative, I mean, algebraically, it's sitting in the same place in both of these formulas. It's a factor, right? Or said differently, the derivative is a thing that allows you to relate input changes to output changes. And that's really the big point of view I want to start with. Here we have a discrete change in the value of the input. Here we have a rate of change of a value in the input. These are different kinds of changes that we can talk about in the input. On the other side, we have changes in the output. Approximation to a discrete change, instantaneous rate of change, input changes, output changes. Right? Derivative is a connection between those two. So we're going to find a bunch of different kinds of derivatives in this course. What they're all going to have in common is, in their own different ways, all of the derivatives we're going to talk about are relationships between input changes and output changes. Right? So, again, forget slopes. Think about relationships between input changes and output changes. Okay. Here's that picture in the graph context. You know, you could imagine if you have some curve representing a graph of a function. If you move over a little bit in the domain, correspondingly it's going to move up in the target. Right, talk about the ratio of those changes. Likewise, if you're moving with a velocity in the domain, there's a corresponding velocity in the target. Talk about the relationship between those velocities. Now, last thing I'm going to do real quick, and there's a few examples in here. The examples are really just straight up single variable calculus examples. It should look very warmed over and familiar to y'all. But I do want to, before, I'm going to skip those examples and let you read them, but I do want to redraw these pictures. These are the pictures that, again, might be more familiar. Again, the reason they're familiar is because they're graphs. And again, we need to, we need to let go of the side of the swimming pool and, try to re-evaluate, re-understand everything outside of the graph context. And all I'm going to do is point out that in both of these situations, I have a domain that's the x-axis. I have a target that I can think of as the y-axis. And my domains, the x-axis, I don't have to draw in the graph context. I can just draw my domains separately. I can draw my targets separately. Right? And so, for example, here is a perfectly reasonable way to think about that previous picture. You move a little bit in the domain, there's a corresponding movement of the target. Likewise, if you're moving with a certain velocity in the domain, then there's a corresponding velocity in the target. I don't need the graph to be able to observe that what I'm interested in is a relationship between these vectors, right? And that's another good observation. While I'm here, let me just point out that in both cases, I'm interpreting these vectors differently, but in both cases, there's a vector in the domain representing some kind of change, what kind of change it is, whatever that is, appropriate to the context, interpret as it makes sense. Vector in the domain that I want to relate to corresponding vector in the target. Okay, so now before we capitalize on what we just talked about, there is one little special case that I need to treat first, derivatives of parametric curves. It turns out that derivatives of parametric curves are an extremely handy way to generalize this idea, right? Input velocity, what is the corresponding output velocity? It's really helpful in order to do that to have an already developed idea of derivatives of parametric curves. So this is a little bit of a, oh gosh, I almost said tangent. That would have been unfortunate. So this is a little bit of a digression, kind of, a little bit, but not that much. Okay, so here's a parametric curve. Parametric curves, right? So we have a function from R1 to Rn. The input variable we very often think of as time. And as a function of time, we have various output variables representing position in the target, Rn. Okay. So, is this a multivariable function, you might say? And, kind of, but also kind of not really. There's something about these functions that's really kind of single variable. There's only one actual variable, right? I mean, everything is a function of t. There's several coefficient functions, you might say, but until you decide you want to, give them names, arguably t is the only variable. Anyway, this is a cosmetic point, but anyway, you could very reasonably argue that this is a lot like a single variable function, and at a minimum. And so with that in mind, we're going to define a derivative of a parametric curve like this. And note how familiar this looks. This is, it's like it's straight out of a Calc 1 textbook, right? Hope that looks familiar to everybody. All right. Somebody were to ask you what the derivative of this function is, not having the slightest idea, the dart that you would fling against the wall hoping that it might hit something would be probably this formula. And you'd be right. That's a very natural guess. Okay, now why do we make this choice? It turns out that this is despite the fact that we're kind of guessing that I don't know, it seems like a reasonable thing to break down. Turns out this is absolutely natural geometrically. Before we get to the geometric interpretation, I want to talk about computations a little bit. Here's how you, in fact, compute them. There's a nice punchline here. Derivative of parametric curve, this limit. If you think about, well, how do you subtract two vectors? Well, you subtract two vectors component-wise. Right? A vector whose components are these minus a vector whose components are these. The result is a vector whose components are the individual coordinate differences. So we say component-wise. So we're doing the vector subtraction one coordinate at a time, one component at a time. So coordinate-wise or component-wise. Okay, now, how do I divide this vector by a scalar, h? Well, we divide vectors by scalars component-wise, one coordinate at a time. That's just how you do the algebra there, right? So that's handy. Now notice I have a limit here. Limit as h approaches 0. Limit of a vector valued function. How do we compute limits of vector valued functions? We do it component-wise. Notice the pattern here. All these individual steps, everything that goes into computing a parametric derivative, all the individual steps are things that we already know how to do, and they're all component-wise. So, nice punchline. Parametric derivatives are computed component-wise. Right? Look at these components. They're all exactly, not vaguely reminiscent of, but they are exactly single variable derivatives straight out of Math 111L. Like so. So that's the really, really good news. If you have a parametric curve given, you want to take the derivative. Oh no, look at this formula. Oh, it's vectors. We're taking derivatives of a vector. Oh, is that going to be somehow harder to do? Nah, just one component at a time, straight up. No big deal. Okay, now what is it? What does it look like geometrically? Here's our parametric curve. I'm drawing this parametric curve in 3 space, and note I'm not drawing a graph. Common mistake for students to make at this point is to think, okay, well, it's the same formula for a derivative. The computations work out nicely. Doesn't it compute like the slope or something? Common point of view to take. Keep in mind, derivatives in the single variable context can be thought of as slopes, but only if you're looking at a graph of the function. We are not looking at a graph of the function here. Here we are looking at the image of the function, not the graph. And there is no t-axis on here. Yeah? Everybody on board? No t-axis? No input variables on this axis system? Not a graph. This is an image. So we're looking at a function by way of a very different geometric construction, and you just cannot sort of carry over, interpret the how does the algebra look in this geometry if you're looking at different geometry. Okay. So what is it then? Here's the idea. Let's look at R of t, some point on the curve, R of t plus h. It's also a point on the curve. It's a little further down the road. But in this numerator, we're referring to 2 different points on the curve. Now we're looking at the difference of those 2 points on the curve. And that difference, it's not a tangent vector. Here, let me use a pencil. It's not a tangent vector exactly. But it's kind of close to tangent, sort of. Right? So, certainly as h gets smaller and smaller, this difference vector, well, it's also going to be getting smaller and smaller. The red point's going to be approaching the purple point. It's going to increasingly approach tangency, but it's not exactly tangent. Okay. All right, now what happens when you divide by h? Well, dividing by h, let's see here, so the difference is in green. Dividing by h, as h gets smaller, as h approaches 0, well, it's probably going to be smaller than 1, so dividing by this small number is going to make the vector longer. So there's this sort of competing forces thing going on here, that as h gets smaller and smaller, the numerator vector is getting shorter and shorter, but I'm dividing by a scalar that is also getting smaller and smaller. And so in the limit, we expect, well, who knows? Right? Algebra will decide on that. But you would not be surprised if there ended up being some vector in the limit of finite length, non-zero finite length. And keep in mind, these green vectors are getting, in terms of the direction that this blue vector points, the green vector, the direction of the yellow vector, is getting closer and closer to tangent. So in the limit, you would kind of expect, or you certainly wouldn't be surprised if it turned out that the blue vector was a tangent vector to the curve. Not a slope. A tangent vector. It's a vector. Yeah. So that's the big conclusion from this picture. You expect the derivative to be a tangent vector to your parametric curve. All right, now what's the magnitude? How long is this tangent vector? Well, if you look at the algebra here, you look at the magnitude of the derivative, and I'm going to sweep a little formality under the rug as to have limits of magnitudes and what happens there. Algebraically, can you move the limit outside of the vector magnitude? It turns out it's fine. What we're looking at is magnitude of a difference vector. Well, that's just the distance traveled along the curve. That's how far is it from here to here. That's a distance. And this represents the time difference between t and t plus h. So distance divided by time, that's speed. Right, so we know two things about this derivative then. This derivative vector, on the one hand, it's a tangent vector. On the other hand, the magnitude is the speed. Now let's think about that. What is this? What does it mean altogether? What is a vector that's pointing in the direction of motion and whose magnitude is the speed? We already have a name for that vector. It's the velocity vector. Okay, so it's a nice conclusion. Derivatives of parametric curves are velocity vectors. Is everybody happy with that? Okay, so suppose we have a bird flying through the air, like so. By the way, we already know what this parametric curve is, right? This parametric curve is the one where the xy projection is doing like this, and then the altitude is just getting higher and higher. So what we have here is a bird who's he's caught an updraft and he's going around in circles, and they do that sometimes, right? So plausible, bird flying on this parametric curve. And we could reasonably ask, what's his velocity as a function of time? Well, we now have exactly what we need to do this. Velocity is derivative. Derivatives are computed one component at a time, as discussed earlier. These individual component derivatives are Calc 1 that y'all are all experts at. Right? By the way, that's going to be an assumption in this class. I'm going to assume that you are high up at the top of your game in computing derivatives, antiderivatives, all that Calc 1 stuff that you successfully made it through and may have been hoping to never see again. It's back. There's going to be a fair amount of it. Chain rule, substitutions, right? Integration by parts. It's all over the place in this class. So make sure that you're strong with derivatives and antiderivatives. All right. So anyway, here we go. Velocity. You take the appropriate derivatives. There's the answer. That's the velocity. Everybody good? Okay, now here's one that's kind of backwards. Suppose you have some moving particle and it has an initial position. It starts off, in other words, at the point 3, 2, 5, and suppose that I know what the velocity is as a function of time. Can we work backwards? Can we reverse engineer and find position as a function of time? Now, I hope this rings some bells, right? I mean, y'all done questions like this in Calc 1 class, or I don't know, Calc 1, Calc 2, somewhere along in there, where you're given velocity and you take the antiderivative and then you, etc., find the constant. It's the same thing. It's morally the exact same thing. The only difference is there are now 3 separate components. So in the same way that velocity is a derivative of position, position is an antiderivative of velocity, which we are given. Right? How do you compute antiderivatives of vector valued functions? Well, it's one component at a time. And the reason for this is, I think, pretty clear. The way you would confirm whether you have an antiderivative is by computing a derivative to see if you got what you're supposed to. And that's done one component at a time. So, morally, antiderivatives are done one component at a time because derivatives are done one component at a time. Okay. So here they are. Calc 1 rears its ugly head. Again. 3 different antiderivatives. I know those are pretty easy ones. Hope y'all remember how to do those antiderivatives. Do be sure to put the integration constants in there. And by the way, do be sure that you don't just say plus c for all 3 of them, because they are different integration constants. They're going to be evaluated in independent ways. They are certainly not to be assumed to always be the same. Right, does everybody see why that is? Right? They're coming from different coordinates of a vector value calculation. So you cannot assume that they're the same. By the way, while we're on the topic of integration constants, please also, there's certain, certain teachers in certain high school contexts, anyway, make some really weird choices about how to deal with C. And I had a teacher one time who told me this. And I was a student at the time who was I to dispute, but at this point I dispute the following. But here was the calculation. Something like x equals t squared plus c. And then let's suppose that we're, for whatever reason, we're going to do some algebra with this. And so we multiply both sides by 3. And I was told that this is acceptable. The argument was, well, we don't know what it is anyway, so it's just arbitrary. It's, constants, and who really cares? So you just, cosmetically, it's just, you have to put plus c because it could be anything. But since we don't know what it is, it doesn't really matter what it is. So 3c is no different from c. They're both unknowns, so what's the difference? Right, so that was the case that was made. Now, let me refute that. Now, at this point, I have 2 equations on the board. 2 equations that I have claimed are true. I wrote them in my handwriting. Right? My reputation's on the line here. And the thing is, I have now got 2 equations, both of which refer to C. And if we ever do solve for C, these 2 things are different. And that's not okay. Right? So please don't make this, this is not okay. Just because you don't know what C is doesn't mean it's not a variable like every other variable, and you've got to treat it like every other variable. I've seen extreme examples of this where students have even done this. They've exponentiated both sides. Like that. Wow. That's really bad. That's not okay at all. There's no sense in which that's at all reasonable. That's just flat wrong in every sense of the word. All right, does everybody see why? Okay, so be careful with your C's. Think it through. Yeah. Okay, now how do we evaluate these C's? Well, we go to the initial value that we were given. We were told that when t is equal to 0, X is 3, 2, 5. Okay, so let's plug that in. Oh, here it is. Do that. Right? So when t is equal to 0, X is 3, 2, 5. T being 0, I plug in to the right-hand side. And all this business here turns into -1, 0, 0. Right, and now you have everything that you need to solve for the C's. And it turns out to be 4, 2, 5. And so plug those back in, and here's your position as a function of time. Please note another thing that's happened here. Another thing that a lot of students come out of high school sort of thinking, and that is that these numbers are always going to be the same as those numbers. And nope. Here's an easy example, right? That's clearly wrong. The reason a lot of students believe that this is the case is because they've done a whole bunch of high school problems where it worked out that way. It was a pure coincidence. It's a pure coincidence based on the fact that, well, very often in high schools, the only functions that you're taking antiderivatives of are polynomials. When you take an antiderivative of a polynomial, the terms, other than the plus c's, all have t's in them. They'll have a factor of t, at least one factor of t. When you then plug in t equals 0, all of these yellow terms turn all into zeros. And so you get all zeros over here, and thus the coincidence that, the c's that you would solve for would equal to the initial values. But that is a coincidence based on the fact that you were looking only at polynomials, right? So in general, it's just not true, right? You got to go through the process and compute what the constants are. The constants not the same as the initial values. Okay. How we doing? Is everybody on board? Okay. Moving along. Very quickly, I want to talk about some of these exercises. There's a bunch of exercises in this section that are all connected to each other. I want to say it's 10 or 12 different exercises that are part of the same large calculation, and it's a calculation about curvature. It's a cool exploration, you might say. I thought about making this part of the section itself in the derivatives of parametric curves section, and having an extra several pages of this stuff. But I think it actually works better as an exercise or as a series of exercises. So what we have is a series of exercises that will culminate in a formula for how to compute the curvature of a parametric curve in 3 dimensions. The details are all in the exercises. Roughly speaking, I'll advise follow the hints. Take the hints and do what the hints say. It will make your lives much, much easier. The calculation that gets us to the result is what I'll call a delicate calculation. This is not, the kind of thing where you can do it a bunch of different ways. You've got to develop these ideas just so, in order for things to work out reasonably. Let me just say it like that. So follow the hint. Do the exercises in the order that they're presented, and follow the hints carefully. So that said, I do want to talk a little bit about what the objects are that are involved. Here we are in 2 dimensions. We start in 2 dimensions. XY plane. So forget about this stuff for the moment. In the XY plane, we have a parametric curve here. And I'm going to ask the question, at this point, what's the curvature of this curve? Now, let me tell you what I'm not asking. I'm not asking, imagine this is a road and I'm driving by in a car. I'm not asking how fast, as I drive, how much am I experiencing, direction change or whatever you want to call it. Because that's the road trip. Right? That's me driving. Maybe I'm a fast driver. Maybe I seems like it was really curvy because I was driving really fast. Right? That's my problem. Right? So I'm asking here about the road, not the road trip. Right, so I want to know how much curvature does the road itself do, independent of whether someone's driving slowly and doesn't notice the curvature, or someone's driving too fast and gets a magnified curving experience. Right? No, that's all anecdotal. The curve itself. So the way we get our hands on that is we talk about the direction that the curve is going. We look at that tangent vector and we ask, well, what is the angle? What's the angle with the horizontal? And I'm going to follow a convention and call that phi. You'd think we'd call it theta, but it would be a little awkward to call it theta because we're not talking about an angle measured from the origin. Right? So we're talking about an angle measured from a different point. It's got a lot in common with theta, but anyway, it would be weird to call it theta. So that angle theta, and you could very reasonably ask, how does that angle theta change per unit distance traveled? And the distance traveled doesn't care how fast you're traveling, right? For each extra inch that you move along this curve, how much does that angle change? I don't care if you did that extra inch in a tenth of a second, or if you did that extra inch in 4 seconds, whatever. It's not a problem. Just do the inch. How much does the angle change? That's what we're interested in. So rate of change of that angle with respect to distance. And I appeal to your geometric intuition. That's going to relate to curvature, right? The more that angle changes as a result of moving along the curve, the more you would say that we have curvature of the curve. So dpds, reasonable choice. Now, how do we get our hands on that? Well, this angle phi, of course. Whoops, I wanted to change colors. This angle phi relates to that tangent line. The tangent line comes from the tangent vector. The tangent vector comes from the velocity vector, and the velocity vector is the derivative. So there's going to be a bunch of calculus, a bunch of derivatives that goes into computing curvature, because the derivative is the thing that is part of the definition of curvature. Okay. So details ensue. Very last thing you're going to do in 2 dimensions is observe that instead of thinking about this angle, you could actually just think about the vector itself. Instead of asking the rate of change of phi with respect to distance, you could think about the rate of change of the tangent vector itself with respect to distance. The rate of change of the tangent vector itself will give you another vector. Turns out it's always perpendicular to the curve. That's something y'all are going to prove as an exercise. And it turns out that the magnitude of this vector, dtds, is also equal to the curvature. It's always the same. So this ends up being convenient. The reason for this is because when you go into a higher dimensional context, so here we are, there's a curve, dtds is this perpendicular vector. In this higher dimensional context, if you say, well, what direction are you going and what angle would represent that direction? There's kind of 2 angles. There's in this kind of sense, which direction are you going? And then there's in this sense. So horizontally and vertically, there's 2 different angles. So which one do we relate, or do we combine them in some way? I mean, it's hard to think about 3-dimensional curvature in terms of angles. It doesn't work well at all. But the derivative of the tangent vector with respect to distance makes perfect sense. Again, perpendicular to the curve. So because this dtds is curvature in 2 dimensions, we're going to define that dtds to be curvature in 3 dimensions. And calculations ensue. It turns out to a couple things that happen, I'll say. There's what we call a plane of motion that are defined by the direction you're going, that's the velocity vector, and the way that you're accelerating. If you think about it, acceleration is going to kind of pull the curve away from the tangent line and off in some second direction. And between the 2 of them, velocity and acceleration, that defines a plane. So the way we compute curvature is the very first thing is we sort of realize we're trying to figure out something happening, even though it's in R3. It's kind of more to the point. It's happening in this two-dimensional plane of motion, and this plane, despite being defined by V and A, it's a lot easier to talk about stuff in terms of these two unit vectors, perpendicular unit vectors, T and N, and the fact that these vectors are unit vectors and perpendicular to each other has some really nice computational consequences, as it turns out. Again, you're going to go through the processes. So there's various participants in, considering the motion within this plane in terms of T and N, and curvature is going to pop out along the way. All right, so details for y'all in the exercises. Okay, moving along. Okay, let me go real quick back to single variable calculus. We had this point of view on the derivative, recall, that whether we're talking about discrete changes, input-output, whether we're talking about instantaneous rates of change, either way, we've got an input vector that we want to relate to an output vector. And, we have an existing point of view in single variable calculus. By the way, I tend to prefer the second one here. I just find it more satisfying. So let's think of these terms here. Think about velocities. If you're moving with a certain velocity in the domain, what is the corresponding velocity in the target? And I want to take this point of view on derivative. So the derivative is the relationship between input velocity and output velocity. I'm going to take this point of view on derivative. Let's try to generalize that now in a multivariable context. We have all the tools that we need. We had to take that little aside with parametric curves. It's done its duty now, and here we go. I want to relate input velocities to output velocities. Okay. So, here it is. Two-dimensional domain, right? Two-dimensional target. And this is a no kidding, no asterisk, no discussion. This is a full-on multivariable function. It's got multiple input variables. Definitely a multivariable function. It even has multiple output variables, whatever. So multivariable function, what would I call a derivative? What should derivative mean in this context? Well, just like we were just talking about, I want to talk about, suppose my input point is moving with some velocity in the domain. What is the corresponding velocity of its image in the target? This is a straight rip-off of the interpretation that we took 30 seconds ago about single variable derivatives. Relationship between input velocities and output velocities. Now, before I do any details, let me just take a pause, make sure everyone's comfortable with that. Does everybody see why this is totally analogous to single variable derivatives, the point of view that we're taking on single variable derivatives? Okay. All right, now how am I going to do that? Am I going to make a physical model of a function and then take my finger, look at the image, and then actually start moving and then try to clock and see what the velocity is of the output? Well, no, of course not. Algebraically, how are we going to get our hands on relating an input velocity and an output velocity? And the answer is I'm going to use what we did with parametric curves. We just got through agreeing that velocities can be thought of as derivatives of parametric curves. So I'm going to interpret this velocity here as a derivative by constructing an actual parametric curve. That's too long. An actual parametric curve. I'm going to make a parametric line just because it's easy. An actual parametric curve for which this is the velocity. Right? I'm going to make this v vector, I'm going to make that dx dt. I'm going to make an actual parametric curve x. That's actually pretty easy to do.
this parametric curve, just write down A plus TV. Now notice that at this point A, right, at t equals 0, what's the velocity of this parametric curve? Well, velocity is the derivative. When you take the derivative, you get v.
All right, so this this construction here, position is A plus TV, gives me a parametric curve that is at the point A and moving with velocity v.
Which is exactly what I wanted, right? I wanted I wanted to contemplate,
suppose I am at this point A and moving with velocity v, what happens in the target? So I now have an actual construction that has me at the point A, moving with velocity v, yeah.
oh, okay, good, cool. All right, so this function then, x is A plus TV. Let's put it into the function. Put it into f.
Right? If my input is A plus TV, my input is this x, x of t function. There's my parametric curve.
Let's just put that into the function, and I get this output curve. I should color code that. I get this output, which is f of x of t. That's going to be some parametric curve.
I don't know exactly what this curve is going to look like. It's probably not going to be a straight line. I mean, I chose a straight line here because I got to choose. If you get to choose, yeah, sure, go ahead and choose a straight line. But the image of this line, by way of this function, who knows what kind of, probably not linear. So this function, the outputs are going to be some other random parametric curve that I've got in blue here.
Now I remind you, why am I doing this? My goal
was, given that I'm at some point A and moving with velocity v, I wanted to know this output point, with my input was at A, the output's obviously at f of A. This output at f of A, if the input's moving with velocity v, I wanted to know what is the corresponding velocity of the output.
The velocity of the output is the velocity of this parametric curve, and that's the derivative
of that f of x of t.
I mean, it's kind of brute force, right? I kind of crammed it in there, but
this is what I wanted. I wanted to know, hey, given a velocity in the domain, what is the resulting velocity of the target? And we have here a formula for explicitly doing that. Make a parametric curve associated to the question, plug into the function to get the output curve, take its parametric curve derivative to get the output that you're interested in.
Okay, so this construction is a very blunt, straightforward construction. Notice the heavy use of derivatives of parametric curves. That's why we had to do 4.2 beforehand. And this makes our definition. I'm going to talk about the terminology in a moment, but this is the first idea that we're going to have on multivariable derivatives. The first real multivariable derivative.
A plus TV is my straight line in the domain. Plug it into f to get the corresponding parametric curve in the target. Take the derivative to get the corresponding velocity.
Okay. All right. So the terminology here, this is called a directional derivative. And note the notation. Actually, let me zoom so I can talk about it. It's called a directional derivative. That notation. It's a directional derivative of the function f. This is the function,
that has certain domains, certain target, input velocity, output. Trying to relate the velocities in the domain and target of that function.
Now you do have to specify where are you taking this derivative. Keep in mind you started at the point A. You got to specify what that point A is where you're interested in the derivative. And you also have to, let's not forget,
I wanted to compute what this output velocity was, but the output velocity with the understanding at the point A that I was moving with a certain input velocity. So this output velocity depends on what that input velocity is. So I've got to represent that in the notation as well. And here we go, velocity V. So it's a bunch of notation that has to get written down. The big D is for derivative. Well, it's either for directional or derivative. Take your pick. I like to think of it as derivative. The subscript of V is telling you, in some sense, what kind of a derivative you're taking. You're taking a derivative, you might say, with velocity, input velocity V. So D sub V says, derivative in the V direction, maybe you might want to say. And yeah, you're taking this V derivative of F, but you're computing that V derivative of F at the point A. That's the base point where you started at. Okay. So that's the notation, and that's how you compute it. Oh, one last thing. Let's talk about this, at t equals 0. Why do we compute the derivative at t equals 0? Let's go back to this picture. Keep in mind the purpose of this green parametric curve here. The purpose of that parametric curve is to help me describe something very specific, namely being at that point and moving with that velocity. I really just needed to be at this point and moving with that velocity. I don't need to actually be, over here. I'm not interested in what's happening over there. Couldn't care less about what's happening way over there, right? So we're interested in what's happening here. We are at that point A when t is equal to 0, right? So t is equal to 0. T equals 0 is what puts me at this point in the domain, and therefore puts me at this point in the target, and it's therefore at that point in the target that I want to know the velocity, aka the derivative. So the directional derivative, this purple vector, it's a derivative of this output parametric curve, but I want to evaluate that derivative at this blue point, namely at the point A, which in terms of t happens when t is equal to 0. But yeah. Mm-hmm.
But then, do we have to keep the whole derivative of x of t at, what I'm not understanding from it is that you have to, plug in the value of x into the function as...
Yep. Oh, yeah. You gotta compute this whole thing. You're gonna take the x of t as a function, plug that function into this other function. We'll see an algebraic example in a moment. But yeah, you got a bunch of algebra to do first before you start taking derivatives. Totally. Absolutely. Okay. All right, so before we start doing the algebra, just a quick sort of final cap on this. Again, just, keep in mind the reason that we're doing all of this is because just like with single variable derivatives, this is the thing that's going to allow us, to relate the idea of an input velocity and an output velocity. It's all we wanted in the first place. And that's why we call it a derivative. Okay, let's get our hands dirty. And I'll come back to a couple of things I want to say about terminology. But let's do one. So here's a function, multivariable function, 3 input variables. There's only 1 output variable, but whatever. Okay, given that function, suppose we're at a certain point in the domain, and we're moving with a certain velocity. What's the rate of change of this function? Now let me put this into context a little bit. Maybe, why would I be interested in such a thing? What does this have to do with anything? Well, maybe I am, let's see here, my domain, R3. My target is just R1. Got this function called f. Let's call these input variables x, y, and z. My output, I don't know, maybe it's, I'm going to call it capital P for the moment. Now, why would that be? Well, maybe my function, f, is telling me
wherever I might happen to be, perhaps in this room, x-axis, y-axis, z-axis. Maybe the function is telling me barometric pressure as a function of location. Right? So if that's the case, why would I be interested in taking a directional derivative? Well, if I were here, a certain point in the room, there's a certain barometric pressure at that point in the room, I could very reasonably ask the question, well, look, I'm moving with a certain velocity in the domain here. I'm not just stuck at that one point. Yeah, at that point the barometric pressure is this, but I'm moving with a certain velocity, and I would like to know what is the corresponding velocity in the target, or said differently, I would like to know how fast my barometric pressure is changing. As I move, I'm here and I'm moving that way, how fast is the barometric pressure changing? Or maybe this is temperature. I want to know how fast the temperature is changing. Or maybe these are three different parameters that have to do with a small business that I'm running, and I want to know how fast is my profit changing if certain economic variables are changing in a certain way. Look at every week, this x variable is decreasing by a certain amount, and every week this y variable is increasing by a certain amount. How does that affect my profits? Right? Very natural questions to want to talk about. Okay. All right. So let's do the calculation. I want to know how fast the output's changing. That's the directional derivative. Let's see here. The function, it was given. My velocity is given, 213 in the domain. Where I'm at to start off, 120. Everything's given. This is all just plug and chug. So here's my definition of directional derivative. Let's start plugging in. A was 120. V is 213. Just plugging in. I haven't really done anything yet. I'm just plugging in. Right? Let's combine that into a single vector. So this is my parametric curve in the domain. This is my straight line in the domain, you might say. And you can check for yourself that this is a straight line in the domain, that when t equals 0 puts you at that point, and that when t equals 0 has velocity equal to that. So this is literally our sort of model line in the domain. Now, what do we do with our model line in the domain? Well, we plug it into the function. So we plug into f. Where was f? Okay, f is that. It's let's see here. I've got to memorize this now. X squared plus yz. So first component squared plus second component times third component. Right? X squared plus yz. And here, what we're plugging in, there's our x. So there you see x squared. Right? And our second and third components, the y and the z, I'm multiplying there. So there's x squared plus yz. Just directly plugging into the function. And then you got to do some algebra. You got, multiply that out, collect terms, whatever you got to do, crank it to get this expression. Okay, so now that is representing, the barometric pressure or what have you as a function of time in the target. So next step, take the derivative of that. Heads up, don't just plug in t equals 0. Please don't plug in t equals 0 yet. You haven't taken the derivative yet. Right? Hope that's another fact from single variable calculus. If you're interested in a derivative at a certain moment, you got to take the derivative first and then plug in the moment afterwards. If you just plug in t equals 0 to start off with, then no matter what this function is, you will have a constant. The derivative will be 0, and that doesn't make any sense. Okay. So we take the derivative. That's Calc 1, easy to do. Now we plug in t equals 0. and we get 10. There you go. Everybody happy? See how the process works? Okay, we are out of time, so I will pick up here. I want to go back and talk about a little bit of terminology and interpretation, and I do have one more example, and then we'll proceed from there. By the way, today is Friday. Today is the last day of new material for the exam, because so don't forget Monday's a holiday. So so the stuff that we're doing today, the stuff that we finished today, is due on Wednesday. The homework is due on Wednesday. The exam is Wednesday. I have to have the homework due at that time because this material is fair game. It wouldn't make any sense for me to allow you to not do the homework until after the exam. It doesn't make any sense at all. Right? Homework's supposed to help you prepare for the exam. Anyway, so the fair game material for the exam, and likewise, the material for today's homework assignment is through section 5.2. I'm not going to put 5.3 because I do want to say several more things about it before we go on. So 4. Yes, thank you. Sorry, section. Yeah, sorry. Didn't mean to freak anybody out there. Yeah. Chapter 4. Yeah. Yeah, I will send an email about that as soon as I get back down to my office. Absolutely. Okay, and I have homeworks